طيب بسم الله الرحمن الرحيم. So last time we started to talk about the physical properties of the wireless signal or the electromagnetic wave in different ranges of frequencies. And we said that in low frequency, the wavelength is very, very large, and that allows the signal to physically be able to penetrate through any obstacle. And as well, it goes into very, very long distances before it actually attenuates or dies. And the higher the frequency, the more effect of attenuation, as well as the signal loses its ability to penetrate. So it tends to diffract or refract, as we will also elaborate today more. And then we started to talk about the three fundamental parameters that characterize any signal, which is the amplitude and the phase and the frequency. We talked about the different visual representation of a signal. We know the time domain of the signal, so we can model the amplitude of the signal and the values with respect to time. We also talked about the fact that the simplest form of a signal is what? Is the sine wave. And the sine wave, if I represent the sine wave in the frequency domain, I can represent using just one impulse that represents the frequency of this sine wave. This is the simplest form. Fourier tried to use or try to derive a theorem where you can really characterize and represent any kind of composite signal using set of sine waves and cosine waves. طبعا by cosine we mean that it's a sine but with different phase. So by changing amplitude frequency, by having different frequency of the sine waves, and the phase by having the cosine here, we can use these multiple signals to represent any composite signal. Okay. So we said that if one thing I'm not sure if we discussed it or not, but if this composite signal is periodic signal, this is very important. If this composite signal is periodic, ماشي, whether it's discrete or not, okay, the signal representation in the frequency domain, they tend to be finite, which means that this is an example of a periodic signal. So we have a period that repeats. So in that case, I can rest assured that it will not be infinity here. I can represent this signal using a discrete set of frequencies. And these frequencies are discrete. Otherwise, I will end up with infinite number of signals, which means that technically the signal representation in the frequency domain, it will probably be something continuous, which means I have infinite values of frequency to represent this signal. The special case of this representation, if the signal is periodic, then I will end up with discrete representation in the frequency domain. Okay? Otherwise, if the signal is non-periodic, then the representation in the frequency domain takes the general form of continuous values. واضحة النقطة دي؟ أي لبس؟ Okay? One thing to remember here is that if the signal has some discrete value like this is apart from periodicity. This sharp change here causes usually infinite values when it comes to frequency. Okay, so you will have usually signal. Of course, this one is periodic, right? And we said it has discrete value, but these discrete values can have infinite values of frequency. They're still discrete, their number is still finite, but they tend to have very, very high frequency component. Okay, so digital signals, and by digital signal here I mean signals which have discrete values in the amplitude or discrete values with respect to the time. These type of digital signals, they have sharp changes, right? Because the frequency here measures the amount of changes in the signal, right? So a sharp change like this causes the change to be يعني very, very high. In that case, you will end up having very high values of frequencies in the frequency domain. However, as you can see here, we represented this signal using only 3 sine waves. So here, this figure shows that we can represent this signal using 3 sine waves. And this is approximation, of course. This is approximation. So basically, this signal has multiple discrete values, which have large frequency components. But usually, if we end up using 3 harmonics only, or 4, or something like this, we have good approximation for representing this value. And that's why if you reconstruct this value at the receiver, if you reconstruct this signal at the receiver, usually you end up with something like this. Okay? You see, the sharp changes, they have been smoothed out.
Even
right?
this is too ideal.
Eh?
Even this is too ideal.
Yeah, in a way, true, yes. But it's good enough for me because here, this is a digital signal, right? Digital signal, I just need to know whether the signal is 1 or 0. And this is clearly, this is very easy. If you have a threshold, you can detect the ones from the 0 easily, right? And that's what I need. تمام? So based on that, we have talked about the different visual representation of a signal. So this is the time domain, okay? And the time domain here can give you some idea about the values in the time domain as well as the phase. It doesn't give me some information. It doesn't give me any information about the frequency representation, and that's why we have the frequency domain representation where the sine wave can be represented using one impulse. So if I have multiple sine waves, I can have digitized or discrete impulses to represent these different sine waves. This visual representation, probably unless you have taken Network 2 or any previous wireless communication course, this is called the IQ diagram. So this type of visual representation, it gives me some idea about the phase of the signal, okay, and the amplitude. So, and each sine wave in that case is represented using a dot, one particular point in the IQ diagram. This kind of diagrams, it helps us a lot to understand how we can derive probability of error when it comes to composite signals which have different phase values, because each one is represented using one dot. So if you have different dots like this, okay, each of these points, they represent one sine wave or one sine wave with certain phase shift in the time domain. Okay, so in the IQ diagram, they look as points, and then based on the difference between these points, we can sort of derive some probability of error, as we will see. So this visual representation helps us a lot. So also we'll start to talk probably next lecture about digital modulation, like by ASK, FSK, and so on and so forth. Some of you already have some idea from Network 2. So we'll drive the probability of error for these different digital modulation schemes analytically this time, and we'll get into some math. So digital signals, they need infinite frequencies for perfect representation. And of course, one of the things is that, okay, all right, so all of this have been discussed last time. Maybe we forgot to highlight some one issue or two issues. But now the topic of today is the antennas. Antennas is a brand new topic for many of you. We did not study antennas in Network 1 or Network 2. Antennas, of course, is the is the unit that radiates the electromagnetic wave in the air, and based on that, I can detect this signal on the other side. So, or electromagnetic wave on the other side, and then from this electromagnetic wave, I can try to detect how the data looks like and so on. These antennas and the radiation that goes out of these antennas, they have also certain properties and characteristics which we need to understand. So for starters here, we know that the ideal antenna is just a point or a small sphere in the air, which tend to radiate electromagnetic wave in all 3D, okay, with the exact same homogeneity, or it's the same basically. So if you measure the electromagnetic wave from any place or any point in the same sphere, okay, you will find it pretty much the same, right? So this type of antennas is practically infeasible, and it's not valid, and it does not exist, okay? So we don't have this antenna in practice. It's just a theoretical way to, to be able to understand or comprehend that electromagnetic wave can ideally radiate in the 3D in the air in a form of a sphere, and at any distance you can have certain signal strength, okay, in this particular distance. Ideally, I should have a homogeneous pattern of electromagnetic wave, okay, in certain distance, but practically this is not achievable. Okay, so this isotropic radiator does not exist in practice. So in that case, real antennas, or the practical implementations of antennas, they always have directive effects, which means that the radiation, okay, is not the same in all the 3D space. It's not the same. It cannot be the same. It needs to have certain shape, okay, and it's different from one location to another. Okay. So the most common or the oldest type of antenna is what we call the dipole antenna. Dipole antenna ده اللي هو on the Land Cruisers is very, very common. People, they have this long antenna, right? And they tend to raise it up, and we'll talk about why they make it the longest possible. But this is the most common or the oldest type of antennas. Of course, nowadays antennas are just less than millimeter on our phones. These can be different antennas. And of course, our phone, by the way, this contains maybe tens of these antennas in different places. And we'll talk about this. It's called MIMO. Okay, so we'll talk about this. So this dipole antenna, since it's like a post kida, so from top it has sort of a 2D homogeneous radiation, but not 3D, right? So in top view kida, it has like sort of homogeneous, of course not ideal, but homogeneous radiation. But from side view, from any place, it has this shape. Okay. واضحة ليه? Okay. So in a way, this is directed antenna, and this is in practice, 100% of these antennas are directed.
The one in the middle is the top view?
Yes, this is the top view كده.
Because it says side view.
Yeah, well, it's relative. It's relative. top or side ماشي مش هنختلف. المهم إن it has different views. Okay. If you look at it from here, it looks like a circle, but if you look at it from any side, it looks like it's a sort of a egg-like pattern. So the most important thing is that it's directed. It's directive. It's not isotropic. ماشي? Sometimes we call this omnidirectional in 2D plane, but not in 3D. Omnidirectional means that it radiates in a homogeneous shape, but this is only in 2D, okay, but not in 3D. The 3D is called isotropic antenna. طيب, so another type of directed antennas is what we call sectorized antenna. Okay, sectorized antenna is yeah, you can think of it as multiple antennas, which each one is actually has certain direction, and then you sort of integrate 3 or 6 or 8 of them, okay, in one integrated antenna. So the pattern looks like this. Or this is for 6 sectorized antenna. There is, of course, very common circular antenna. Circular antenna needs to or tends to have something like this. It's like a circle, but this circle is composed of minute little antennas which form like a circle, right? So antenna radiation بقى looks يعني زي, it's like a flower كده يعني. This is the circular antenna, okay? Many of the base stations that we use, they use sectorized antennas or circular antennas, whether 8 or 12 or circular antenna. This is the most common, especially in base stations, the deployed base stations. So if you notice the base stations, you always find there is like a big post, and then on top there is like different antennas. Each of them is like directed antenna, and they form like a circle. Okay, so they are all directed antennas. Very important characteristic for the antenna, as we have discussed before, there are 2 types. For the dipole antenna, there are 2 types. The dipole antenna can be fed from the middle, so the energy comes from the middle, okay? In which case, this length is lambda over 2, or should be lambda over 2. So if the signal that you are trying to feed has a specific lambda, then the length of that antenna is lambda over 2 to have efficient communication. If it's less, you may still have communication, but it's not efficient. And that's why people, they tend to extend especially if you're listening مثلا to a radio FM, or because FM we're talking about relatively low frequency, 88 megahertz or something like this for FM and AM. FM is in the kilohertz even. So طبعا with 88 megahertz, the lambdas, they tend to be fairly long, and that's why you need to extend the dipole antenna very, very long to be able to have efficient communication or listen to high quality signal. واضح ليه؟ If it's fed from here, if it's fed from bottom, then this is actually lambda even over 4. This is lambda over 4. So the length is lambda over 4, which means you need to extend even more. Okay, so so in the characteristic of having lambda over 2 or lambda over 4 limits the type of signal that you can feed to this antenna in order to have efficient communication. And that's very important, and that's why we tend to increase the frequency in order to reduce the size of the antenna. But we know as we increase the frequency, there are some impairments that start to happen, such as quick attenuation. The signal does not penetrate. Okay, we have what we call shadowing. We'll talk about this. Okay, so the signal gets blocked through some obstacles, and in some cases you have reflections, and reflections يعني again introduce what we call multipath fading. We'll talk about this. So we start to have impairments back. Okay, so that's why in the past it's very easy. It was very easy to deal with low frequency, but the problem is the scale of the device. The scale of the devices that we are talking about. That's why in the past, maybe you didn't live these days, then FM stations يعني submarine communication, everything is like very, very large scale. Okay, because of this. Okay, as life becomes more complicated, we started to have small form factor devices, right? And that restricts the type of signal that you can feed to this, which means that the signal has to be high frequency. But in high frequency, we have these challenges. We have shadowing, we have deep fading, and so on and so forth, right? But luckily, as science evolved, we have been able to deal with this multipath fading. We'll talk about some techniques, yani. Okay? So we can even use this multipath fading sometimes as a benefit, not as a challenge. So in some cases, we can actually use it as a benefit, but that requires huge amount of intelligence. Okay, we'll talk about this. Another thing is that we have the antenna diversity. Antenna diversity talks about the fact that in many devices you have more than one antenna. Okay? Nowadays, we have, as I said, like tens of antennas on just one cell phone. So also we have some limitation when it comes to the separation between the antennas. So also the separation between the antennas is lambda over 2. And that has to do with the fact that, remember, this is actually the lambda is like the distance that the signal can travel in a period, t, صح? This is the definition of the... So if you have lambda over 2, it's like the two signals are something like this. Okay? So it's like the phase between them in the air is clearly distinguishable. Okay? So that's why you need to have clear separation between the antennas in order to have efficient communication. Okay? So if as I said, if the dipole antenna is fed from the bottom, then this length is only lambda over 4. But the separation between the two antennas has to be lambda over 2. So now, if I have multiple antennas on one device, that creates what we call antenna diversity. بمعنى إيه؟ Now, at the receiver side, the receiver has multiple antennas, and each antenna sort of absorbs certain energy from the environment that represents the signal that is coming over the air. واضح?
Like covering different angles.
Yeah, yes. So they have special diversity, or there is certain separation between them. Each antenna can detect certain energy depending on its directionality, of course, right? So each antenna absorbs certain energy from the electromagnetic waves that are coming in. صح? Okay? طيب. The receiver side, how does it deal with that? So I have different energy absorbed by different antennas, right? So I can use this multiple receptions from the antennas using different ways. One of them is called switch diversity. بمعنى, switch diversity is that the receiver would say, if I have multiple antenna, I would try to measure the energy level on each of them. Okay? And the one that gives me the highest energy, I will just use the signal coming from that particular antenna. This is the easiest. This is the easiest. And this is very simple, but it gives me high quality reception compared to single antenna. Of course, because single antenna, you have one possibility. But now, if you have n different antennas, right, you will go through them, O of n, basically, you'll go through them. And the one that gives you high energy, I will say this is the one. But maybe after few seconds, another antenna will have the maximum, right? Because, again, it depends. It depends on the location of that antenna, on the directionality, and on many factors, right? Some of these antennas, they absorb different levels of energy, okay? And of course, below certain energy level, the signal that you will receive is not detectable. خلاص, you cannot detect anything out of it, okay? So it becomes really hard. So that's why the receiver tries to switch to the antenna that gives you the highest energy. So this is the one that will make the reception and the detection of the signal very easy. I can detect all the ones and zeros easily from that signal, right? Because the energy that is coming in is maximum. this is the simplest. This is the simplest way, right? But of course, as you might imagine, what if I combine all of them? If I combine all of them, I get even high energy. Well, maybe yes, maybe no. Why? Because combining all of them, okay, might have some of them, they cancel each other because they are not co-phased. صح؟ يعني you receive a signal like this and another signal like this, they will cancel each other. So do not try to be not intelligent and say, okay, so I will combine all of them, right? Blindly كده. لا. If you want to combine all of them, yes, you can, but you need to be careful in that case. You probably have to do some processing to the phase of some of these signals in order to really make them co-phased. In that case, you can combine them and have the highest energy. So that, of course, complicates the receiver significantly, as you can imagine. So the receiver then will have to process the signal that is coming from each antenna separately before it combines them, صح? So that's why combining has to be co-phasing is needed to avoid a cancellation, right? So there are, by the way, different ways of combining these the signals that are coming from the different antennas, and not just based on the phase, and based on the amplitude, and based on some other factors. We're not going to get to the details of this, but there is something called maximum ratio combining. There are co-phasing. There are so many techniques and ways for how you can combine the signals together. But the idea here is that we're not selecting one in that case. We have to combine the signal coming from all antennas at the same time. But sometimes I need to multiply each signal with a factor, okay, which allows me to get the best SNR or signal to noise ratio. We'll talk about this for the overall summation of all these signals together.
Professor, there is no redundancy in combining?
Not redundancy. This is not redundancy. This is, or if you think of it as redundancy, this is good redundancy. And the idea is that if I have multiple antennas, I can use these multiple antennas to enhance the reception. This is my objective, right? It's redundant in terms of hardware. Of course, you have multiple antennas, but that's needed. We always use redundancy to lower the probability of error. صح? It's like fault tolerance. Fault tolerance in networks, we sometimes replicate different parts of the network, right? So if one path has certain problem, we go to another path. صح? But this is redundancy, صح? But we are using this redundancy to try to minimize the probability of error, or we try to have some fault tolerance. So if the system has certain problem, we can still function efficiently even if that problem happens. So this is similar. So the signal that is coming on a particular antenna might suffer, as we will talk in a minute, might suffer deep fading, right? And that's for this time instance. Maybe after 2 seconds, it will be different. Okay, so if I rely on one single antenna and there is deep fading, then I don't have reception. خلاص, I'm done. Okay, so this is yes redundant in terms of hardware, but I'm doing this for the sake of a efficient reception. واضح؟ تمام؟ طيب. Now we talk about the concept of MIMO, or multiple input, multiple output. So MIMO here talks about the fact that I have multiple antenna at the sender and at the receiver. So we talked about multiple antenna at the receiver side, and we discussed how we can use that to enhance the reception. MIMO here talks about the fact that if I have multiple antenna at the sender and multiple antenna at the receiver, what are the possible combinations that again allows me to maximize the reception or increase the efficiency of the reception? So multi-input, multi-output uses بقى several antenna at the receiver and at the transmitter. So they use that concept to not only بقى increase the reception, or enhance the quality of reception, but in some cases they use that to increase data rates. To increase the data rates. How بقى? So, of course, this concept MIMO has been introduced in 802.11n and in LTE starting from generation 4 or 4G, as we will talk later, and HSPA, اللي هو ال high speed packet access. We talked about this before and we'll talk about it later in more details. So this MIMO allows me to have different techniques. One of them is beamforming, and beamforming على فكرة is very, very common technique, which allows you to optimize the reception at certain point by controlling the transmission. So how do we do this? What happens here is that we have multiple antenna, okay, which they have different distances between them, right? So one thing I could do is that I can, this is redundant برضو, I can transfer the same signal, okay? I can transfer the exact same signal, a copy of the signal. I can transmit it on all these three antennas. But هو الidea بقى, I will transfer the same signal from the three antennas with the objective that at this point these signals will arrive at the same time, such that if I have at the transmitter, if I have a signal, I start now here, and then I start the other one a little bit later, okay? And I start the other one a little bit later, something like that, okay? These signals, they start from the transmitter at slightly different time. But I know that because of the fact that these distances are different, okay? This time difference is proportional to the distance between all these three antennas and the reception point, in such a way that when they arrive here, okay, of course there will be a difference in time. So this difference in time is accounted for at the transmitter side, okay? Because we know that this antenna, for example, this antenna, low antenna 1, if I transfer the signal from this antenna 1, this signal will arrive here within a time frame T1, okay? So if I transfer the same signal, okay, from antenna 2, the signal will arrive at the same point at time T1 but plus D1 or D2 مثلا, okay?
Is there guarantees that this will happen? That they will
هو yes, I can estimate that. I can estimate that because ما هو بقى somehow
This is fixed between the sender and the receiver. That's
إيه?
why. Because the distance is fixed.
Yeah, the distance is not fixed between the sender and the receiver. The distance, I'm talking about the distance between each antenna and the other antenna at the receiver. The distances between the antennas, right? Because the antennas at the sender, they have some separation between them. صح? So the distance between each antenna at the transmitter and this particular antenna at the receiver is different, slightly different, okay? So the idea here is that I can estimate that difference in time, and then I can introduce that difference in the transmitted signal. So that I know that if I transmit these signals like this from the different antennas, by the time they arrive here, they will be exactly co-phased. واضحة دي؟
Because the distance between the three is different.
Exactly. Okay. So if I know بقى إن هما ده مثلا the sending time here, I can send one at time T0 and then I can send this at time t0 minus d, right? So this is t0 minus d, remember, plus the flight time, صح? The flight time is what? Is t1 plus d2, صح? So this d2 هتكنسل d2 خلاص يبقى هتوصل in the exact same time. واضحة كده؟ واضحة؟ تمام؟ يعني I'm trying to play with the receiver يعني.
This is too ideal, right? Because whatever.
Of course بس احنا of course على فكرة co-phasing احنا هنا we're talking about the ideal case, of course. You are perfectly right. But I'm trying to really minimize the out of phase between the signals. It will never be 100%. And by the way, we never seek 100% quality, especially in wireless communications. It's almost impossible. But we are trying to always minimize the effect, minimize, not eliminate. Okay? So we're talking about this ideal case just for the sake of explanation. But of course, in practice, there is some difference or shift or something like this.
I wasn't considering the time itself, but maybe obstacles in the way or something that might actually just.
Yeah, this is different. This is different issue. We'll talk about this. لو shadowing و fading وكده, we'll talk about this in a minute. And of course, you're right. It affects برضه المايم طبعا. Okay? But theoretically speaking, if we can control this at the sender side, all of them, they will arrive at the exact same time in this point. So it's like you are steering a beam, صح? That's why it's called beam forming. واضح كده؟ That's why it's called beam forming. Beam forming is one of the very, very يعني common and core techniques in wireless communication in general, starting from I think third generation wireless, 3G. Beam forming is يعني. So MIMO has been introduced in 3.5G and 4G. ماشي؟ تفضل. Of course. That's a very good point. So, of course, this is the ideal case if the transmitter and or the receiver are moving. Okay, the challenge here بقى is how to adjust this and estimate the distances between the antennas dynamically in real time. Of course, this is an issue. Of course, that's an issue. Is it possible? Yes, it's possible. It's possible. Okay, even if they are moving, because here we're talking about يعني less than millisecond level. So how do we estimate the distances? Signal strength. We know how to do this. صح? Signal strength. If we know the transmitted power, it's known. Okay. خلاص, we measure the signal strength. We can estimate the distance more or less. Again, there is some يعني measurement error, but we never claim that this is يعني perfect. ماشي كده? But is it possible? Yes, it's possible. So this is beam forming. So I'm trying to optimize the reception at a particular point or points. ماشي? So I can use that by for my benefit. Even if they are mobile, I can definitely control the power and the phase shift on these antennas to control where and how to get the optimized reception at certain points. ماشي كده؟ Sometimes they use حتى beam forming to try to minimize the blind spots مثلا in wireless coverage. So if مثلا you do some surveys and you know that there are some blind spots in certain areas, okay, so I can control I can use beam forming to steer the beams in order to really have coverage, wireless coverage in these blind spots. Okay, I can control بقى خلاص معناها I can control. So in the space I can optimize the reception quality at certain point using beam forming. Okay. Type. So the beam forming is one of the MIMO techniques. We also have special multiplexing. Special multiplexing here is slightly different. So beam forming is the objective for it is to optimize the reception quality. Special multiplexing, the objective for it is actually to increase the data rates. How? So I get the same signal at the transmitter, I get the signal, and then This signal is what? It represents digital data, صح? Ones and zeros at the end. Okay? I can split the digital data, right? I can divide it by 3 or by 4, depending on the number of antennas. So I get substreams, صح? And then these substreams, I can send them now on the separate antennas. Okay? In that case, I don't have to do beamforming. خلاص? So the antenna here, antenna 1, will be received by antenna 1 here. Antenna 2 will be received by antenna 2 here. So this is what we call spatial diversity. So I can split one data stream into 3 or 4 data streams, in which case I can send, of course, as you can imagine, I can send more data stream, okay, just by using this splitting, right? So that can be used to increase, in that case, the data rates using special multiplexing. So beamforming, we're talking about the same copy of the signal being sent, but with some pre-processing to control the phase of that signal in order to allow them to arrive at the same time. Special multiplexing, we don't do that. We actually split the actual data into multiple streams, and we send each streams on individual antenna. So in that case, I can essentially raise the overall data rates. Okay, this is the concept that's used in 802.11n, and 802.11n can reach in the gigabits per second by using this is one of the enhancements that they used in 802.11n. ماشي كده؟ And there is diversity coding. Diversity coding here talks about the fact that the same when we controlled the phase of the signal, right? Why? Because these signals will be superimposed in the air, will be some in the air, and then I can receive these signals here on the receiver side, and they have to be co-phase. So this is a phase processing. Okay, sometimes this phase processing is complicated from the transmitter side. The implementation in terms of hardware is a bit complicated. So another way of doing the same objective, right, but without having to do this complicated pre-processing for the phase is what we call diversity coding. So diversity coding is slightly similar to beamforming. However, instead of, so each signal here, so in beamforming, this signal 1 will have to be transformed into signal 1 dash, and this signal is actually a phase shift for signal 1, right? And then in the air, at the receiver side, I get a S1 dash plus S2 dash plus S3 dash, and hopefully, when I get this summation, and they are co-phased, then I get the maximum reception, right? So that's what happened. Diversity coding talks about a slightly different technique. I get S1, instead of transforming S1 to S1 dash, I don't do this. I do S1 times code 1. That's why it's called diversity coding. Okay? S1 times code 1 plus S2 times code 2 plus S3 times code 3. The idea here is that at the receiver side, I can receive each signal, which is the exact same copy of the original signal, but I can receive them separately at the receiver side. I can separate between them as I wish. And I can do this by co-phasing, or I can do this processing. أعملها بقى post-processing instead of pre-processing.
So like the concept of encryption.
Yes, هو أصلا this is diversity coding here is similar to CDMA if someone has been introduced to CDMA, or code division multiplexing or code division multiple access. We'll study this again in this course. The idea of code division multiple access is that you multiply a signal with a code, and these codes, they are orthogonal. That's why here you find the word orthogonal. So these codes are orthogonal. So at the receiver side, this actually gives you the ability of being able to distinguish between them at any point of time. Okay, so one antenna can have code 1. If you multiply this by this, then you get S1, and all of them will be cancelled. We'll talk about this. Yani. In any case, we can separate these signals at the receiver, and then we can do post-processing at the receiver as we wish.
The antenna should be pre-designed so that they get the data about C1, C2.
Of course. In that case, the antenna, of course, the transceiver that is connected to the antenna needs to be designed in such a way that it has these codes, and it deals with these codes. Okay? So there is a slight difference between beamforming and diversity coding. Okay? But both of them, they talk about the same copy of the signal, and both of them, they actually focus on enhancing or optimizing the reception quality. Unlike spatial multiplexing, which focuses on increasing data rates. واضح? Because we have to split the digital stream into multiple substreams and transfer each substream on a separate antenna. So the objective here is to increase the data rates. ماشي? Any question? طيب. Now, we talk about signal propagation ranges. This is also quite important, especially when we talk about ad hoc communication or any kind of peer-to-peer communication. We need to know the ranges and the ability of us to detect the signal at each of these ranges. So if a transmitter tries to send a signal, assuming that in 2D we have omnidirectional, in 2D we have omnidirectional, okay? So the sender sends with a specific transmission power, okay? This allows the signal to travel in the air, and of course the signal, when it travels in the air, the signal will start to attenuate, صح? So at certain levels, if the signal attenuates a lot, it becomes undetectable, okay? Which means that the level, the maximum and the minimum, the distance between them, or the gap between them, starts to shrink in such a way that you cannot really distinguish the ones from the zeros. It becomes really hard, right? So that's what defines these ranges. So the sender, when it sends with a specific transmission power, you have what we call transmission range. In this transmission range, the communication is possible, which means that the signal does not attenuate a lot, okay, which makes the receiver able to receive the signal with low probability of error. Okay? واضحة دي؟ سهلة. تمام؟ And there is detection range. The detection range, I can still at the receiver side, I can still detect the signal. Why? Because still the energy of the signal is slightly above the noise range. Yani there is a noise floor, okay, below which I consider this noise. And of course, the air is full of noise, of course, okay? Because as we speak now, there are hundreds of wireless signals are being transmitted here and there from base stations, from this and that. صح ولا لا? Okay? But in certain points, if you try to detect this signal, you will find the signal levels is below an energy level, and you consider this noise because you cannot detect anything out of it. In the detection range, still the signal energy is above the noise level. Okay, this is problematic. Why? This is problematic because we cannot say that the reception is not possible. The reception is still possible, but with very high error rates. Okay? So this is the detection range. The signal is detected, but it has very high probability of error to be able to distinguish the ones and the zeros and read the digital data out of this signal. واضحة؟ And there is بقى interference range. Interference range, the signal may not be detected بمعنى ان هي بقى the signal is below the ايه the threshold, we consider it a noise. صح؟ يعني if we try to extract ones and zeros from this signal, probably the error will be 100%. But that doesn't mean that the signal does not exist physically. واضح؟ A signal still exists, but يعني عاملة كده مثلا. It's still there, صح? But I cannot really detect anything out of this. But why this is important? Because this is an interference range, because it actually interferes with other signals. So it increases the probability of error for other signals in the air that it tries to communicate efficiently with low probability of error. So this interference range معناها the signal interferes with other signals. واضح كده؟ يبقى الترانسميشن signal is transmitted high power levels, and يعني معناها the signal to the noise in the air, the signal is really high, and any noise cannot affect it that much. So the probability of error is low. In the detection range, the signal starts to get close, still above the threshold that we consider it noise, right? But because the gap between the signal and the noise starts to shrink, right? So the signal to noise ratio shrinks. And in that case, the probability of error goes high. Okay? So in the interference range, it becomes really noise. So the signal to noise ratio becomes almost 1.
I would imagine that the transmission distance from the sender and the direction would be smaller distance from the sender than the transmission. But from this graph, it's the same. How?
Yeah, this is idealistic, طبعا, of course. But of course, actually, what you are saying is not a theorem. I mean, it could be actually equal. It could be the same. So just to give you an example, مثلا, if we try to talk about Wi-Fi, okay, Wi-Fi مثلا has a theoretical range of مثلا 50 meters, okay. But if you look at these 50 meters, you will find that this 50 meters actually includes the transmission and the detection range. So above مثلا 30 meters, you will probably have very, very, very high probability of error. Above 50 meters, of course, you will have zero communication. That's why the range is like 50 meters. But usually 50 meters is actually idealistic. You will not get good level of communication at 50 meters at all. Usually it's 30 meters. And of course, that also varies depending on the environment. خد بالك لأني we'll talk about now the effect of these obstacles on the signal, right? So if I try to have Wi-Fi communication in this room with all these obstacles, is different, right, from having the same type of communication in outdoor and there's no obstacles. The transmission range would differ from one environment to another. ماشي? So that's why we have clear definition for these ranges. Transmission range, we have clear definition. Detection range, we have clear definition. ماشي? But what is the exact? لا, it depends on the environment. It depends on what transmission power you use. It depends on so many things. Okay, so it's not a fixed number. ماشي? Any questions? طيب, signal propagation. This is not completely new, but we need to also have clear definitions. Wireless signal, because of the fact that we cannot maintain the communication in very low frequency because of the limitation of the antenna size and so on and so forth. صح? So we want to scale down the device, the form factor. So we have been enforced to use high frequency communication, right? So starting from 900 megahertz or 800 megahertz, that's why in GSM you have GSM 800 megahertz, 900 megahertz, and we have مثلا اللي هو اسمه ايه ده GPS مثلا. GPS works in the range of 1.2 gigahertz, something like this, and then we started to have 2.4 gigahertz. So these frequency range, اللي هو ISM band, these frequency ranges are fairly large that the wavelengths start to get small, in which case we can have very small form factor antennas and we can have efficient communication. However, this is where the problem that starts to happen. The signal suffers what we call fading. And what fading has multiple ways. So all of these are fading. So fading is the general term that might be caused by shadowing, reflection, refraction, scattering, diffraction. All of these are things that can enforce the signal to have certain type of fading, right? So shadowing here talks about the fact that in certain high frequency range, the signal gets blocked completely. If the signal tries to penetrate an object, and this object, the condition here is that this object is large enough, okay, larger than lambda over 2. ماشي? So if that object is large enough, proportional to the lambda, okay, then the signal fails usually to penetrate that particular medium, and that's what we call shadowing. By shadowing here, we mean that the signal gets blocked, and there is, of course, slight level of energy that gets reflected, but this reflected signal is not detectable anyway. Okay? So it's as if the signal has been completely blocked. But from any medium, depending on two things, the size and the density of that object. The size and the density of that. This is very important. Okay? There is certain percentage of the power that gets completely absorbed, and there is certain percentage of the power that gets reflected. Okay? So in most of the cases, the signal is absorbed and the reflected power is insignificant for the cases where the object is large and the density is high, in which case the signal fails completely to penetrate and it suffers what we call a shadowing. Okay? Shadowing is actually, sometimes shadowing is not bad. We'll show you why. We'll show you cases where shadowing is actually it's not bad. It actually reduces the complexity of multipath fading. So we'll talk about this. There is a reflection. So the difference here is that maybe the object is large enough, yes, but the density is not that high. So the object itself has low density, in which case the signal will not be completely blocked. So the reflected signal here, of course it has less energy, but it's significant enough that you can have some reception out of it. Yani if you have receiver here, and you have the transmitter here, right? So the transmitter will send the signal, it will get reflected, and the receiver here can still detect the signal. Okay? So this is reflection. Refraction talks about the fact that there is certain percentage of the signal that actually penetrates the object. Again, depending on two things, the size and the density. Okay? So that typically happens مثلا for under marine communication, for water, if you have the transmitter above the water and you have a receiver under the water. This is a very common scenario. Okay? Another very common example is satellite communication. Because in satellite communication, you have satellites that send wireless signal, right? And usually if you have higher density, the signal tends to get close to the high density object. So if we imagine, مثلا, we have the air above the atmosphere, because around the Earth we have the atmosphere boundary, right? So the atmosphere boundary you have higher density here and lower density above, right? Which means that when the signal comes from the satellite, it usually gets in Earth. It does not deviate out of Earth, which is good. And that's what we need, صح? To have satellite communication, this is exactly what we need, right? Also, this is good news for also if you have a sender above water and the receiver underwater, right? So the signal will not reflect away. It will reflect inside the water, and you can have some communication.
Also the case for the clouds or the raining clouds. The same.
Right? Yeah, in a way, yes, yes. The signal can penetrate through the cloud because the cloud usually they have low density. But clouds can also cause this. We call this by scattering. This usually happens when the frequency starts to get by in the tens of gigahertz. Okay, in the tens of gigahertz, usually the signal will not reflect in one direction. It will reflect in multiple directions. So we call this scattering.
What is an example of such a signal?
Any signals with يعني حتى in Wi-Fi مثلا 5 gigahertz 5 gigahertz, and that's why in 5 gigahertz, by the way, the range is lower, right? Because the signal in higher frequency, they tend to have a scattering. They tend to again attenuate faster, because the attenuation also is proportional or inversely proportional to the frequency, right? So not only the signal attenuates faster, it actually suffers from scattering, and that makes the range of or the transmission range less. ماشي كده؟ So this usually happens in the 5 or 10 gigahertz or 30 gigahertz or something like this. So above certain limit of, if you have مثلا 60 gigahertz or something, usually you cannot have communication unless you have line of sight. Why? Because يعني any dust in the air can cause scattering to the signal. Even dust in the air can cause scattering for the signal, right? So the only way is to have line of sight and you have high transmission power. That's when you have some type of communication. That's why millimeter wave is not, as far as I know, يعني, it's part of 5G. Millimeter wave is part of 5G, and we'll talk about this, right? But it's not deployed until now. Why? Because it's very high frequency. We're talking about 60 gigahertz and something like this. And usually the scattering in these frequency ranges is very, very high and very common. And you need to have almost line of sight in order to have communication. But if you have line of sight, you can have very high data rates, because it's like laser. Well, it's like you have laser communication, basically. Okay. Of course, diffraction is the same. It's like if it hits like a tip of the mountain. So diffraction is relatively similar to scattering, but here the object size might be a little bit bigger, but because of the fact that you have difference in density between the tip and the air, you may have this scattering effect, or in that case we call it diffraction. You see? So all of these are different forms of signal fading. So all of these are called fading effect. What is the effect of this, Ba? The fading causes interesting phenomena here, which is called the multipath propagation. Multipath propagation here talks about the fact that if you have two signals like this in the time domain, you have two signals with this difference between them. These are two signals transmitted from the transmitter side, right? If we don't have any obstacles and we have vacuum, okay, so you should expect to receive these two signals like this, maybe something like this, and another one like this. Usually that's what happens, right? Here we're talking about vacuum, which means that there's no obstacles whatsoever, right? But typically that's not the case. So here, multipath fading here talks about the fact that if the signal is going in omnidirectional like this, so basically you have many paths for this signal. And some of these paths, they may hit some obstacle and get reflected or scattered, right? So what happens, or gets reflected from here or reflected from this object. So what will happen is that what will arrive here is multiple copies of the signal with some deformation, right? So these two pulses here, for example, they reach to the other side looking like this. So the black three copies here, they represent this pulse. And the orange ones, they represent this one. So it's three copies that corresponds to these different paths, right? واضحة كده؟ واضحة؟ Okay. So what will this cause? This will cause what we call this a symbol. We call this a symbol. A symbol is like whether we send 1 bit or maybe 2 bits. And we'll talk about digital modulation where we can represent 2 bits using different amplitude or different phase. In any case, we call this a symbol, right? So when we transmit a symbol and the symbol suffers from multipath propagation, right? We have the phenomena of a inter-symbol interference. Although they were not overlapping at the transmitter side, but because of the multipath propagation, they actually overlapped at the receiver side, right? So the receiver now has to deal with this. And of course, this inter-symbol interference causes some probability of error, right? So how can I مثلا mitigate something like this? Any ideas? How can I mitigate something like this? How can I fix it? Cancelهم ازاي؟ So the only way is to try to avoid, or يعني one of the ways is to try to avoid this overlap, this inter-symbol interference. One of the ways is to make these two symbols away from each other, right? So the more I get them away, the more I reduce the effect of the multipath fading. Because if these are separated with large distance, even if I have multiple copies like this, there's still separation between them. They are not overlapping. So the inter-symbol interference becomes less. But of course, in that case, I'm lowering the data rates. Why? Because if you increase the separation between them, essentially you have to reduce the symbol rate, which means reduce the data rate. واضح? So that's a trade-off. So this is a trade-off. And of course, this is not something that you can easily estimate. Because here, imagine بقى if كمان, as you said, imagine if this car is moving. So the multipath that we're talking about will change in real time, right? So that's why I'm saying that as we increase the frequency, there were serious implications, and we had to deal with that. And that's why the wireless communication field has become more and more sophisticated to try to deal with all these issues, right? مفهوم كده? Any questions? So this is the phenomena of multipath propagation and inter-symbol interference. طيب. With the effect of mobility بقى, this multipath propagation can cause different effects, because this multipath propagation will entail the fact that you have different copies that arrive to the receiver, right? And because some of them are going in a straight line, some of them are reflected, right? So in that case, these reflected signals will definitely have some phase shift, which means that the multipath or the multi-copies, when they arrive at the receiver, they may arrive out of phase. معايا ولا لا? They may arrive out of phase. If they are out of phase, they will cancel each other. ماشي? So the mobility can cause two well-known phenomena, at least in wireless communication يعني, اللي هو short-term fading and long-term fading. Short-term fading here talks about the fact that as the car moves, the multipath propagation causes at certain point the signals will arrive out of phase and they will cancel each other, so you have drop in the signal like this. And then in short time it goes up again. As the car moves, you have short-term fading. It goes down a little bit because the signals are arriving out of phase, and then it goes up again. ماشي? And then it goes down, and then it goes up again. So this short-term fading causes big trouble, of course, because with short-term fading, the signal drops, the signal energy drops very low, and it becomes, in some cases, undetectable, but for a short period of time, and then it goes back up again. واضح? So this is what we call short-term fading. Long-term fading talks about the fact that as the car moves away from the transmitter, right, the effect of fading becomes slow. Why? Because if the signal, if the car moves in a straight line, right, so there is another fading that happens because the signal attenuates as it arrives to the receiver. So if the car is moving away, right, the signal attenuates as it arrives to the car, and in that case, the fading is long-term, which means that it doesn't happen like sharp drops like this. It decays but slow. So this is what we call a long-term fading. So it does not drop and then goes up. It does not drop and goes up. But this is the effect of path loss. So there are two very common effects that happen to the signal. There is the path loss, and that's why we'll talk about path loss model, and we'll talk about fading model. Path loss model here talks about the fact that as the signal moves away, it attenuates, yes, over time. Okay? And of course, this attenuation, the speed of this attenuation is proportional or inversely proportional to the frequency. Right? ماشي? So this is one effect, low path loss effect, and there is the short-term fading effect when the signal moves and there is multipath that arrive. When they arrive out of phase, the signal drops and then it goes back up again. So this is a short-term fading. ماشي? So the distance to the sender and the obstacles further away, they cause the phenomena of long-term fading. ماشي?
In this case, where the power goes to zero.
Not zero, not specifically zero, but if they are out of phase, it drops. Not specifically to zero, but it drops drastically. And of course, the way we deal with the short-term fading and long-term fading, the techniques are different. ماشي كده؟ طيب, any questions so far? We can have a break, and then we can come back to the... Okay, so to continue the discussion, here we'll talk about multiplexing. And by multiplexing here, we mean the fact that we have a common shared medium, whether this common shared medium is wireless or wired. So in wireless, by default, the air is shared. In wired, we could have the same thing, okay, where multiple users are sharing this. And this happens, for example, in Ethernet, where we have a shared medium, and all the users are sharing this medium. So in that case, we have to use multiplexing, or a strategy for how to mix the signals that are coming from these multiple nodes or users. So there are four common ways or four common categories of techniques based on which we can do this multiplexing in general, so in wired or in wireless. The reason is I cannot send from two users on the shared medium at the same time, at the same frequency, right? I cannot do that. If I do this, what will happen? We'll have a collision, what we call collision, right? So I have to have certain variation between the multiple users. So this variation can be in four different forms. So we can divide the shared medium in space. How do we do this? So if we have a guided medium, then we have to use two different guided media, ماشي? One for each communication. So we separate them by space. Okay. For wireless, how do we do this?
The guard band.
Guard band. لا, I'm talking about special space. Separate them in space.
Each one use different bandwidth.
لا, the frequency.
Different line of sight.
Different line of sight. عشان يبقى في line of sight, we use directional antenna, right? So we can use these directional antenna. Each antenna will send in specific direction, right? And we can have separation between these directions. So in which case we can have two communications going on at the same time, but they are not affecting each other because they are in the space. The electromagnetic wave is traveling in different directions. واضح كده? So this is the space. So we can separate the users in the space. We call this usually spatial diversity. ماشي? So multiple users can use the space, right, and send in different directions, and we can have multiple communications going on at the same time. Okay. So if we have like, imagine if we have 4 people, or 2 of them are talking to each other. Okay. So, and they are talking the same language, same everything. So if 2 are communicating using English language and the other 2 are communicating using English language and they are close to each other, the 2 receivers may not be able to distinguish, right? So we'll have a high level of interference or, in a way, collision. Yeah. Okay? So we don't want to do that. So imagine if they separate that, if they get further away, right? If they get far enough, خلاص, the receivers can listen and they have no problem. So this is spatial diversity. So we use the space, right, as a way to separate the communication. Sometimes we use the time to separate the communication from each user. So in other words, we have, as we said, we have a shared medium, right? And we have multiple users. So we'll allow these users to take turns. Okay? So each user will take a small period of time, and the user can have the shared medium dedicated for him for this short period of time. Okay? And then we go to next, and then we do another round and so on. ماشي? So it's like round robin. So in that case, we can have no collision. So we divide the shared resource in the time domain. So we can divide it in the space, or we can divide it in the time.
Like a delay in the previous.
Right, yeah, so each user has specific data to send, right? So we need to organize that. It's like we are in a meeting. Imagine we are in a meeting by now. Okay, so we have shared floor, right? And we're trying to have a meeting. So if everybody tries to talk at the same time, we'll have noise, right? But if we come to the meeting with the intention at least to organize ourselves, then we say each one will have a time slot to say whatever he or she wants to say, right? And then it goes to next, and then it goes to next, and so on. ماشي? So this is dividing the shared medium in the time domain. So we know how to divide it in the space. We know how to divide it in the time. We can divide it in the frequency. So 2 communications can happen at the same time, okay, if they use different frequency. And that's what we called before a broadband communication. So for example, if we talk about the voice communication, the voice itself as a signal, it usually has a bandwidth of 4K. And we call this the baseband. And it has 0 frequency component. This starts from 0 frequency all the way to 4K. Not exactly 0, but يعني starts from very, very low frequency all the way to 4K. Right? So that's why if 2 people communicate with voice at the same time, okay, they will collide. But this is baseband, right? But if we take بقى the same voice signal and then we have two communication, they overlap in the baseband. However, if we separate them in frequency, this means that we'll take the first one, we'll shift it in frequency so it becomes like this, and then we take the other one, we shift it in frequency, it becomes like this, and we separate them using guard band in the frequency domain, right? So in that case, there's no collision, no overlap. I can distinguish easily one from the other by using a filter bar. I can filter out and I can extract one signal from the other. So there is no overlap in the frequency domain, right? So in that case, the shared medium will be divided in the space domain, and sorry, in the frequency domain, not in the time, not in the space. Okay? So these are three well-known, easy. We can distinguish them, right? What is this about fourth one? We divide the signal in the code domain. Okay? This is this is the entrance to 3G. 3G started to use that concept. It was a revolutionary concept. We can allow the communication to happen at the same time, at the same frequency. Okay? So if we go back to the example that we have four people and each two are trying to communicate, right? In order to really perceive this and understand it, if the two communications happening at the same time, same language, and they are talking same language, right? Then there will be high level of interference and they cannot distinguish one from the other. So imagine bad, if two people are talking in Arabic and the other two people are talking in Chinese, right? Why Arabic and Chinese? Because there's no correlation whatsoever between these two languages. These two languages are very far apart aslan. There's no correlation whatsoever. Yani if Arabic and Persian, I would say, okay, so there is interference, right? If Arabic and English, yeah, there is less amount of correlation. If Arabic and Chinese, there's no correlation whatsoever. So imagine if two people are talking in Arabic and two people are talking in Chinese, okay? The one on the other side understands Arabic and the one on the other side understands Chinese. Can the two communication happen at the same time? Probably yes. صح? Right? Because the two languages are very far apart. They are not correlated whatsoever. So how can we use this concept in wireless communication? What happens is that what we do is that we use codes. These codes are nothing but, digital data, right? So if I want to transfer one signal مثلا with high amplitude, I don't transfer just one. I code this one into a code that looks like this. Okay? What is the benefit now? I can design code 1, code 2, code 3, and code 4. I can get each signal and multiply it by different codes. Okay? So what is the gain here? In the shared medium, we will get the summation. We'll get the superposition of all these signals all at the same time, right? So they clearly overlap in time and frequency. Okay? But what is the trick here? The trick is that these codes are orthogonal compared to each other, which means that there is the correlation of one code and itself is very high, طبعا. And the correlation of one code and the other is zero. There's no correlation whatsoever. Okay? So if we get a signal, if we get the composite signal, we get the composite signal, which is S1C1 plus S2C2 plus S3C3 plus كذا كذا. Okay? At the receiver side, قلنا بقى the receiver knows Arabic or the receiver knows Chinese, right? So if the receiver knows Arabic, he has the code. It's like encryption. ماشي? He has the code for Arabic. ماشي? So he multiplies this code with the composite signal. What happens is that when I multiply this by code 1, the correlation will be high, which means that the signal will be very high. But when I multiply S2 times C2 times C1, the answer is 0. S3, 0. S4, 0. So the correlation of this code with itself only is high, and with all the other codes is 0. Okay? So the codes are orthogonal compared to each other. Orthogonal معناها إيه؟ The correlation between a code and all the other codes is 0. So the multiplication is 0. واضح? So this is the example in real life. So you select two different coded languages which are very far apart. There is no correlation between each other. ماشي? So in practice, what we do is that we design these codes in such a way that they are orthogonal, which means that correlation with itself is high, correlation with all the other codes is 0.
So if we look at the two codes, the ones from this side will correlate with the zeros from the other side, vice versa.
Right, yeah, and if you want to receive signal 1, then you need to have code 1. If you want to receive signal 2, you need to have code 2. Which means essentially that the receiver may have multiple codes, right? And depending on whatever signal he or she wants to receive, he needs to have the code for this signal. So there is that code management and code distribution. There is that. There is of course an issue or a management issue that comes with this. But in any case, this is conceptually how we divide the shared medium with respect to codes. واضح? We divide them with respect to codes using the phenomenon of orthogonality. Using the phenomenon of orthogonality.
But does this not limit the number of signals that can be sent?
Of course, the frequency does the same thing. It limits. We have limited spectrum. In fact, this is the motivation behind 3G, is that theoretically speaking, in a small area, okay, within the same bandwidth, you can have potentially thousands of orthogonal codes. Thousands of orthogonal codes. Whereas if you want to divide this spectrum with respect to frequency, we'll end up with limited number of frequency channels. Which means essentially you can achieve very high spectrum efficiency using the codes. So that this was the biggest motivation towards 3G. Okay, so 3G, they increased the data rates using this concept by increasing the spectrum efficiency using orthogonal codes. Of course, there is there are scientists who design these codes in such a way that they are orthogonal, like Hamming codes and so on, and they started to prove the orthogonality, and so there is a huge amount of signal processing, and we're not going to get deeply into this, but we'll explain again the code division multiplexing, which uses that particular concept. ماشي? It's very important to notice here is that whether we talk about frequency or time or even code, there is a guard band. Guard band is needed. Why? ليه بقى؟ لسه مكلمين دلوقتي. ليه؟ Why?
Avoid interference.
Interference due to ايه؟ أيوة, due to particularly multipath fading or multipath propagation. Because multipath propagation creates multiple copies of the signal, ماشي? Which it extends the time or the frequency of the signal. Okay? So in order to avoid inter-symbol interference, you need to have these guard bands, whether in time or frequency. ماشي? So this is very important. Type. So frequency. So we have a frequency multiplexing. We need to analyze. If we divide the signals in frequency, what are the pros and cons? We need to get deeply back. ماشي? What are the pros and cons? Separation for the frequency, separation of the whole spectrum into small frequency bands. the channel gets certain band. So we have يعني a shared medium has limited spectrum. Of course, there is no such thing having infinite spectrum. We'll talk about this spectrum regulation. Usually operators, they pay hundreds of millions of dollars to just license specific spectrum. So it's a very critical issue. ماشي? So I cannot have infinite spectrum. يعني. طيب, so channel gets certain bands of the spectrum for the whole time. So a user can have the channel or the shared channel, right, all the time, right? But using the concept of broadband communication, this user will have to use limited or certain frequency range. One issue or one challenge with this is that typically these frequency ranges, I can divide them between the users in a fixed way. Okay, in a prefixed way. يعني. بمعنى I can allocate these frequency ranges to the users, right? And then I don't need any coordination or any centralized control. So everyone knows what frequency to send through, and that's it. So that makes it simple, but the problem with this becomes the channel utilization. بمعنى ان I assign a specific frequency to a user, and this user does not have any data to send at the moment. ماشي? So I assign the frequency range, and the user never used it. واضح كده? So it's as if we are in a meeting and everyone is allowed to use certain frequency range, but certain people, they don't have anything to say, which is, it happens. ماشي? So this can actually work in analog or digital signal. The concept itself is very general. Once you allocate certain frequency, you can have this for any type of communication, whether analog communication or so this concept was actually used in generation 1, even for the amps. You can use the concept of frequency multiplexing even for 1G. Okay? But 2G we'll start to talk about the sophistication here. One of the disadvantages here is that, as we said, it's a waste of bandwidth. And it's inflexible in the sense that once I allocate these frequencies, it's not easy to just change. I say, okay, Omenna does not have anything to say, so let me give the frequency range to another person. لا, it's not. It's not like this. مش بمزاجك. It's inflexible. So we predefine the frequency ranges for each user, and that's it. ماشي? Of course, that was rigid and inflexible. And of course, in 2G, they started to make that dynamic. We'll talk about how. So with respect to time, if we talk about time, in that case, the channel, the whole spectrum of the channel, is used by one single user, but for short amount of time. ماشي كده؟ طيب, the advantage of this is that only one carrier in the medium. So there's only one carrier. يعني معناها ايه? In the frequency domain, the shared medium has this spectrum range. Okay? So there's one carrier frequency for the whole spectrum. It's like when we say GSM 800. 800 megahertz is actually the carrier frequency, right? So using TDMA, there's one carrier frequency for the medium, and that's it. But for FM or frequency multiplexing, no, there was sub-carriers, because each node will have to send in separate frequency range, and each one has a different carrier, right? So we have main sub-carrier, and we have sub-carriers كتير, صح? Or we have the main carrier frequency, and we have sub-carriers. ماشي كده؟ But in TDM, we don't have this. خلاص. So we don't have this phenomenon. So it's one one carrier frequency for the whole medium because I don't have to divide in frequency, I divide in time, right? So it's one carrier frequency, and we access this the whole spectrum for a short period of time. ماشي? So throughput will be high طبعا for many users, but again we have the same issue that sometimes slots may not be used because we have a round for the user and the user doesn't have anything to send. برضه نفس الشيء. The same inflexibility exists because again these time slots are predefined and it's not flexible enough that I can have a certain period of time allocated to another user easily. لا, it's fixed. ماشي? But hereby there is another issue. There is even another issue, which is precise synchronization is really necessary. Why? Because خد بالك يعني whenever you have multiple nodes, okay, are trying to use certain time instances, there is an issue. Why? Because each of these users, they use independent clock. Each user uses his own or her own independent clock, right? So if I ask now two people, what is the time? Maybe at the minute level there is high possibility it will be the same, but if we go down to the second level, you will find some differences. So this is the same. If we're talking about a short period of time where the channel is allocated to a certain user, chances are each user uses his own clock. And if we have any clock drift, this may cause نفس الissue بقى intersample interference. ماشي? Or may cause interference between these nodes. So synchronization is needed in that case. We're not saying that it's impossible. There are techniques for this. But there has to be some synchronization between the nodes. One of them is to use a centralized clock. ماشي? Like our phones. Our phones use GPS مثلا to synchronize the clock with the satellite. صح? That's why when we move from one country to another, you see the times على طول changed. So your clock is synchronized with some centralized clock, right? So that's the same. So you can use any kind of centralized clock or coordinated clock for all the users to make sure إن هو time periods are synchronized. ماشي كده؟ Any questions? واضح؟ So this is a time division multiplexing. In 2G بقى اللي هو GSM. In GSM they started بقى to have some dynamic behavior. It's because they said allocating the frequency all the time in a fixed way is not efficient because there's no way you can guarantee that you allocate a frequency all the time to a user and he always has data to send. You cannot guarantee that. And sometimes you talk over the phone and then you leave the headset and leave. So you're not using anything. You're not actually saying anything, but you're consuming resources. We don't want this scenario to happen because we want to have maximum utilization to the network resources. Okay, so we want to avoid that scenario completely. So that's why in 2G بقى, they said that we will use time and frequency multiplexing, which means that they divide the channel both in frequency and time. ماشي? Not only that. So first, I will divide the channel in time and frequency. So I create what I call a resource unit كده. And this resource unit meaning that I use a specific frequency range for a short amount of time. Both, right? And not only that, on top of this, they allocate these resource units بقى dynamically كمان. And that بقى requires very highly complicated coordination. Okay? This is complex. Why? Because I have to have like what we call a super frame. A super frame, let's say a super frame like we have a large boundary of frame which spans like 10 seconds for the entire spectrum. ماشي? We call this a super frame. This super frame needs to be divided both in time and frequency, right? So every super frame, first, what I need to do is that I send to the nodes saying, do you have data to send or not? ما أنا مش عبيط بقى. يعني عندك data, I will allocate some resources. You don't have data, I will not allocate resources. So we're trying to be efficient, right? But this will allow you or will force you to have some kind of overhead. So at the beginning, first, it's like we're coming to the meeting, okay? There's no expectation for who will talk or who has certain issues. So at the beginning, we have a moderator, okay? He or she would say, okay, so let's say in the next 5 minutes, who has anything to say? Raise your hand. Okay, so you go first, you go second, you go third. ماشي? So you have 1 minute, you have 2 minutes, you have 2 minutes. معناها you have 1 resource unit and you have 2 resource units and you have 2 resource units. It doesn't have to be equal. It doesn't have to be completely fair. ماشي? Because fairness is not absolute, right? And then after 5 seconds, I would say, oh, okay, so in the next 5 seconds, 5 minutes. In the next 5 minutes, who has anything to say? Okay, Amru, Mamduh, Ali. Okay, so Amr, you have 2. Mamduh, you have 1, okay, and so on. So each super frame, we start to first ask the users, okay, and then based on that, we say, you have two resource units, you have 1, you have 3, you have this, you have that, and then we move to the other super frame and so on. ماشي? So that requires so much handshaking going back and forth. واضحة النقطة؟ So that's what we started to use in 2G. So let alone what happens in 5G. طيب, so in terms of advantages, طبعا it's better protection against tapping. And what that means is that I can dynamically allocate these resource units, which means that if someone wants to read a signal from a specific user, he might be puzzled because sometimes this user sends in a specific time, in a specific frequency. Sometimes he sends in another frequency, in another time. So tapping means that I want to tap or I want to listen to a particular user. So good luck by trying to find this user in this whole grid of transmissions. Okay? So this technique, combining the frequency and time, has the flexibility or has the feature of better protection against tapping. برضو protection against frequency selective interference. And what that means is that imagine if we use frequency multiplexing, which means that we have allocated predefined frequency range for the users. صح? We said that, right? Frequencies or selective interference here talks about the fact that the interference in a specific frequency range is not the same across all ranges. This is normal, صح? So in certain frequency range, we may have interference more than the other. So this depends on how much communication is going on within this range compared to the other ranges. The effect of multipath propagation and so all these factors will cause the fact that the interference for a specific frequency range will likely be different from the other ranges. صح? So when I allocate or I predefine the allocation of frequency for users, this is not fair because some users will suffer from very high frequency ranges and the other users, they don't have any interference. صح? So by default, interference is selective. واضحة النقطة دي؟ So interference is by default selective. Some frequency ranges will suffer deep fading. Some frequency ranges may not actually suffer a high level of interference and so on. So when I change this dynamically, so one of the factors I can keep in mind is how much fading and interference exists in this frequency at this time. Okay? And that's exactly what happens in 2G. So when we say that in this super frame, we say who has data to send, but also we have some state or some observation from from the medium or from the channel how much interference happens in the different frequency ranges at this point of time. Okay? So this interference, I can estimate the probability of error in this frequency range at this time. And based on that, I say, okay, so I will give this resource unit لعبد الرحمن because عبد الرحمن, he can tolerate some يعني error, يعني he has some error tolerance. Or maybe he's using video, high definition video, and maybe if he has certain error does not cause يعني much trouble to the video because certain dots will disappear, that's fine, it's a big deal, no problem. Something like that. واضح? And in another super frame I can change. So frequency selectivity or interference selectivity can be avoided in that case. One user can get a resource unit with deep interference, ماشي خلاص. For fairness, for the next super frame, I will give him a better resource. So it's like معلش يعني خليها علينا. Next time I will give you a better deal. واضحة النقطة؟ طيب, what is the disadvantage بقى؟ طبعا you can imagine the amount of coordination needed. You can imagine the amount of coordination. It's very highly complex, very complex.
This is only on 2G.
This is only on 2G. Imagine بقى in 3G and 4G and 5G. So the coordination here is done يعني similar to what we say. So for each super frame, there is, of course, like some beacons that happen in the beginning, which is sent to the users. If the users, they have anything to send, then they send back some response that I have this data to send. From this response, I know two things. First, user X wants to send this amount of data. Two, how does the signal look like from me to that user? Which gives you some indication about the level of interference in this for this particular user. ماشي? So based on that, I say, okay, so I will give you this resource blocks or this frequency and this time for this super frame and so on and so forth. So every time I need to have this prior subframe for allocation before users they start to send any data. So that's an overhead, and I use that for coordination. واضح كده? Any questions? So this precise coordination is highly complex. Another phenomena which started to emerge بصراحة around maybe 20 years ago. We did يعني heavy research in this area. For some reason it decayed in terms of, but it does exist in starting 4G. يعني there is some existence to cognitive radio, and what that means is that this is good for computer engineering guys مثلا, because before this everything was hardware, and electrical engineering guys, they were dominating, and they had their best time. Okay, so this causes some transition that we can have radio in software. So we can have software-defined radio. And the motivation behind this cognitive radio is that we say, or the largest organization for spectrum allocation or spectrum regulation in general, it's called FCC, Federal, I don't know, Communication something. FCC, in the US طبعا. So what they did is that they released a very critical report that the spectrum, in terms of frequency and time, okay, is of course occupied by different types of communication. For example, مثلا we're talking about TV broadcast. That's radio communication. It uses maybe 800 or 900 megahertz. Of course, GPS, it uses 1.2 gigahertz. We have this in 5 gigahertz. So they did this very, very large, wide-scale survey, ماشي, for the spectrum utilization in different times of the day, okay, in different frequency ranges. And the result was at that time was like eye-opener. It was shocking to many people. Why? Because they found out that there are certain time periods and frequency where the communication is really, really dense, right? And the interference is really high. But what's more shocking is that they discovered that there are certain spectrum ranges which are rarely utilized, and they have no interference, okay? And even the vendors or the organization that licenses this frequency range, they don't tend to use it most of the time, although they have this range licensed for them, right? So that was the motivation behind cognitive radio. And what they said is that we can make the radio more intelligent. Okay? بمعنى, we know that 900 megahertz is occupied by مثلا GSM. We know that, right? But not all the time. Maybe in peak times during the day, the radio is jammed, ماشي? But there are some other times the radio is rarely used. Okay? So what if we allow secondary users or some users who did not pay for that spectrum to be intelligent enough to know that this radio is not used during this time, and they use it unofficially. Okay? So if we can do this, this will be really great, because this will allow us to have high spectrum utilization. ماشي? But what is the challenge here? There are multiple challenges. طبعا this user did not pay, so what is the incentive? That's one. The other thing is that this secondary user, he may have to send to different frequency ranges at different time. صح? And he needs to know that frequency range that he or she should utilize at this point of time, which requires طبعا حتى sometimes it requires he has to sense the channel, he has to know whether there is a primary user who's using that spectrum at this time. If the primary user is using the spectrum, خلاص, all of us, we have to abide. We cannot use the spectrum because this primary user paid thousands of dollars. So we agree, he has the highest priority, right? But if he's not using it, first of all, how do we know that he's not using it? By sensing. We sense, we measure the energy level and so on, and then we say, okay, so he's not utilizing it. But the other problem is now the radio layer becomes highly dynamic, because now I need to send here or here or here or here. And the only way I can achieve this is in software. Why? Because in hardware implementation is usually rigid. So we keep talking to you about the fact that physical layer and the data link layer are all in hardware, صح? Why? For speed, right? And what is the implication of this is that both these layers are inflexible, they are rigid. They are very rigid, right? So I cannot dynamically كده on the fly change the frequency range as I wish, because this will change the whole game, right? So I cannot do that. So the only way for me to do this is to do it in software. But the problem is that software is usually slower, right? So that created the whole paradigm of cognitive radio. We worked on that for like 7 years or something in terms of research. And it was a very, very hot area of research. And we have cognitive radio, cognitive relays, and this was part of 4G. And
is it possible to sense wireless
course.
network?
of course, why not?
Then why we have SISMA CA?
هو SISMA has sensing أصلا.
No, collision avoidance.
Yes.
We don't have collision detection.
Yes, we don't detect collision, but we can sense the channel طبعا. في sensing. في السيزما CA في sensing. ماشي؟ But the problem is that السنسنج هنا has high probability of error. لأن طبعا you have multiple signals coming from different ways, and then you don't know whether this is one signal or two signals or three signals. ماشي? So collision cannot be detected, but of course the signal can be sensed. ماشي? So here we have the primary user, the guy who is like high priority. He paid thousands of dollars and he has the right to use the spectrum at any point whenever he or she wishes, right? And we have this secondary user. This secondary user uses the concept of software-defined radio. This user has to be smart. If you want to access the radio for free, you have to be really smart. And you have to be careful. We don't want to cause interference to the primary user. ماشي? So that caused the paradigm of software-defined radio. Software-defined radio here talks about the fact that unlike the normal physical layer and data link layer implemented in hardware, no, now with software-defined radio, even the physical layer is implemented, or at least good part of it is implemented in pure software. So all the signal processing techniques and application layer, of course, and all the higher layers, these are all software. So we do all the signal processing, we change frequency on the fly using software, we have all types of intelligence. Spectrum sensing, by the way, many people use machine learning for that to increase the accuracy and so on and so forth. They use even the concept of collaborative sensing. يعني there are tons of research work that has been done in this area, cognitive radio. And then once we agree, I know exactly the frequency range that I want to use. I use it as a secondary user, and I did all the precautions that I need to do. Then I produce the signal, and then the signal using digital to analog converter bus. It converts the signal into analog to be transmitted over the antenna. This is the only part that's hardware. All the signal processing, channel line coding, everything is done in software. Okay? The advantage here is that the radio becomes smart, and that's why we call it cognitive, right? The disadvantage is slow, bravo عليك. So we have done actually some implementations using very يعني famous platform called USRP. Universal Software Radio Peripheral, USRP. It's actually a hardware platform that has high speed CPU for all the radio processing and stuff, and it has this analog to digital and digital to analog converters. That's it, for transceiver, for transmission and reception. Okay? So once we convert this to analog, then it goes to the other side, and then we convert it from digital to analog, and then we do the processing and so on. So this is the software-defined radio, which is the means or the technique that we use to facilitate cognitive radio, to have a primary user and secondary user and so on. Type. So these are ways to divide frequency, time, or combination of frequency and time. And as we said, frequency and time here, we talk about spectrum division, and we can use even cognitive radio to provide high level of dynamic coordination between the multiple users to avoid any type of overlap. So the two levels that we talked about is GSM used a combination of time and frequency and used the dynamic allocation of these resource units based on some information from the user, whether this user has data or not, and what is the channel, how does the channel look like for this particular user. And the second level is cognitive read.
Do you have some number there?
Yes. You do have some number. طيب خلاص. وصلت المسج. Okay, so